Okay, reason for me doing this video is because I wanna share with you my understanding of how clustered and non-clustered indexing works. Okay, whenever you hear this term in the database, uh, it, like you always hear that they make the query efficient, much efficient. But yeah, this is actually true. But thing is, you will not like most of the time will not see people get into the details of how they actually work. Okay, so I'll walk through how they work, like the idea behind it, in a short time, like in a quick video here. Before we actually know how they work, we need to know some like uh, some concepts before we go on. Like, okay, first thing we need to know how. Okay, I'm not gonna write this because it's gonna take a lot of time. You need to know how to write, like how data actually gets stored in the database physically. Okay, and beside that, we need to know about a topic called B plus tree or B tree. So we start up with how data gets stored physically. When you end up making a sum table with rows and columns and storing some rows inside it, it ends up physically stored in something called a data page. This data page consists of 8 kilobytes. Like its size is most of the time you see the size of it is 8 kilobytes, and it's constructed in this way. It has a header, a body, or like you think of it as a body, but here where actually rows get stored, and then offset array. No, if I spell this right. Okay. This header, I'm not sure the exact size of each of this block, but you can search about it. Uh, Another thing is like this video is very like these two things that I'm going to explain, the database and the plus B plus tree. You can search for like you can search about it, because I'm not going into the specific details of them. There's like a lot of details that I might miss, but I'm just giving you what you need to understand how indexing works. Okay, what you'd have in the header is a page ID, like normally. You like this. These are parts of it, a page ID, and you'd have the next ID of the next page, and you'd have the previous ID. Okay, and this block where actually rows get stored. Okay, and you'd have this offset array. What it simply does, like it's just an array, but what it does is it points to where the starting offset of the bytes of the array of the rows in the page. Like if you wanna, for example, read the third row here, you'd search, you'd go here and see where this row starts in the block, in this block. Okay. Um, this is simply what, like, this is basically what an offset array is. So this is how actually data gets stored physically. Okay, there's a lot of other details that I didn't cover, like what is an extent and an uniform extent and fragmentation. Like there is a lot of details that I didn't I didn't cover here. You can search of these details. Uh, we are just gonna stick with this. Okay. Another thing we need to know about is B tree or B plus tree. They are two both really similar to each other. Okay. A B tree is a data structure that holds, like, a usual tree would end up having two nodes, but this tree can end up having multiple childs of nodes, okay? This depends on something called the degree of the B tree. It determines the number of child node it has. Like, for example, if I have a B tree of a degree 3, it end up having 3 pointers and 2 keys. Okay. For example, if I have a degree 3, the pointers be like this, and the keys, I'm trying to, uh, like this. This is the first key, and this is the second. Okay. What it does, like, basically what these keys does is this slices the node to help you search in other nodes. Like, if we have a node that consists of numbers between 1 to like 100, we'd have some, if we have here key, for example, number 35 and here 55, what ends up is every node, or like if you want to search for values between 1 to 35, you'd go to this node, okay, to this path. If it's between, you go to this path. If it's bigger than or equal to 55, you end up in this path. And then we'd have the intermediate levels here in this B tree for this data structure, and it ends up with a leaf nodes, okay. And one thing to notice here, or like to mention, a B tree must be in the same, like the leaf nodes of the B tree must end up in the same level. If you keep inserting the levels, or like the upper levels will get, like, it gets growing to the root. Like, if we have, I'm trying to draw a quick one here. If we end up inserting some key here and it doesn't have any space, it will create another level on top of it. Okay, like it. I don't know. Like, I'm struggling to explain this, but okay, I'm gonna pause here and draw something that makes some sense. How do I pose? Um, yeah, I've created some like I've drawn something here that might make sense. Uh, Whenever, like, imagine if we have this B tree, and notice this is just the elements. The number of the elements is not the elements itself. We have a like if we have this B tree and we wanted to insert an element, um, it will end up like gonna look for where it should insert this element, okay? And let's say if it's in the range, like if we have this range and it's bigger than this range, it will go here, okay? But notice is this node does not have any space. So what happens is it takes the middle one and pushes to to the root. But again, the root is full. It takes this and split it in another layer underneath it. The one gets here. The second, or sorry, the seconds becomes in the first root, like in the root, I mean. And then the actual 7 that got moved up gets at the end, okay. And then we insert the 8. Notice is the array gets growing from bottom to up, okay. It gets growing in this direction, not like the usual binary tree thing we see. If we have a binary tree and then when it's insert here, it gets grown downwards. Okay, so this is a quick idea of how binary like B tree works. A B plus tree would end up having a pointer points to the next and to the previous. It's like this. Okay, you can search about it. I'm not gonna like go through all the details. I actually don't know most of the details it have, but I have this general idea of it. Okay, let's keep going. Okay, now we know how data gets stored in physically, and we know B trees. Let's get to the main idea of how cluster and non-clusters indexing works. Okay, whenever you have a table and you have this column, for example, the ID, and you create a primary key or a clustered ID on this column. Okay, what happens is the database engine creates a B plus tree behind the scene for this column. Okay, it doesn't have to be of degree 3. I'm just drawing it for simplicity. It depends on the architecture of the engine. It creates a B plus tree or B tree in behind the scenes, and the nodes itself is a data pages. That like the pages, like I mean the nodes itself is just a page. Okay, and we said earlier, I can spell this, whatever. We said before that a data page consists of a header, uh, rows gets stored here, and array of sets. What happens is whenever you search with a specific ID, it goes through all this by B tree and starts searching. Okay, we have, for example, Seri 4. Okay, uh, it's bigger than, like if we have here, for example, 1 and 2, it's bigger than 2, so we go for this pass. And then if we have more passes, like for example, Seri 4, um, if we have here, let's say 30, uh, 35, for example, it is between, so we go for this pass until it ends up uh, in the leaf node. Okay, what happens is the actual leaf nodes consist of that. Like in the end, the leaf node is like as I said before, it's all data pages. Okay, the actual data gets stored in the leaf nodes. If you search with a if you search with an ID and ends up in the leaf node, then it goes, okay, we have this leaf node, we need the ID of the row number 34. Let's start looking here in the array offset. I mean in the array, the offset array, and and it would go. I'm not sure if it's sequentially or it searches or it gets to 0 somehow, but it ends up looking for the offset of the specific row and then goes to that row. Okay, this is how clustered index work. And yeah, if that's how actually clustered index work. This is if you search with an ID. Okay. Um. Yeah. Okay. Now it comes to non-clustered indexing. Let's say we have a table, and this table consists of a column of some name, like a name column. Okay, and you made a non-clustered ID on this column. What happens is it creates the same structure as have we seen here. It creates a B tree. But what happens in the leaf node is it stores something called an R. My mouse slips. RID. Like it would uses the name to get to the exact leaf node here that has the name, and then it will compute something called an RID. What it stands for row identifier. Or sorry, it does not compute it. It actually gets stored in the data here in the rows. Okay. And another thing I forgot to mention is a leaf node here is named as locator. It's called locator. I don't know if I spelled this correct. What it does is it stores the RID. What happened? Okay, wait a minute. Let's stop the record here. Okay, I just clicked Control R and it made a refresh for the entire whiteboard. I don't know why. Whatever. Let's keep going. What happens is in the leaf nodes, whenever you create a non-clustered index on some column, what happens in the leaf nodes, it creates something called allocator. It's just a database that stores in the rows the name, like the data you actually made non-clustered on, and the RID, which stands for row identifier. Okay. It then uses this row identifier to look for the actual row you're searching for in the data. I mean in the hard disk. Okay. It uses this row identifier to get to the right page that has the actual data you made. Okay. This is how non-clustered works. Okay, what if we have a table that doesn't have any indices, like it doesn't have a non-cluster, neither a clustered index. What happens is like this table actually called a heap table. Okay, what happens is the data pages gets uh, stored in a non-ordered manner in the disk, like imagine some salt, you know, if you have some salt on a table, it like it spreads out, like it's not in an order way. This is how data pages get stored if you have a heap table. And like for example, if we have like if you then searches for a name, and again it's a heap table, it would go starting with the first page. It would search for that name in a O of n time, in a linear time. Okay, it uses the thing I mentioned before, the ID, the next ID, to get to the next page, and I don't think it uses the previous or the like. It uses the ID of the. We'll get to that. Again, it uses a next ID of the page to get to the next page, and it searches like it's a, you can think of it as a uh what is it called, a doubly linked list. It does the same, okay, until it finds the name you're searching for. It finds the row of the name you're searching for. Once it finds this row, it creates or computes something like the thing we mentioned before, the RID. The RID, like how it gets computed, it uses the file ID the data page ID. As I mentioned, every data page has an ID in the header. It uses this ID in the RID computation. Data zoom in. How do I? Okay, it uses the data page ID, and it uses the row offset. As I mentioned before, it uses the offset array here to search for the rows. Okay, once it finds the rows, it uses that row slot or yeah, it's a slot number. Okay, it uses it in the computation of the RID. Once it computes the RID, it stores it and keeps going in through all the pages on finding more matches of the column you searched for, and keeps computing the RID and store it. Once it searches through all the data pages, it then uses this row IDs it stored before to retrieve the results for you. Okay, and I think this is what I wanted. This is all I wanted to cover. Uh, I know it might be not perfect, but I'm not really used to speaking English or making videos, so I'm actually gonna make more videos of these in the future, so I get used to it. Okay, thank you for watching.